All right. So it's important to keep in mind everything that is involved. So there are layers of information when defining mathematical objects. So here we're just defining mathematical objects in terms on the layers of integers, like mod and congruences, etc. But here we have on the layers of sets on the other part here. So it's important to keep that distinction in mind. So first, what we will do is that we'll assume that A is congruent to C and prove that the equivalence class of A is equal to the equivalence class of C. So let's do that. So we have the following proof. Assume that A is congruent to C mod n, and we want to show that the equivalence class of A is equal to the equivalence class of C. So let B be an element of that equivalence class. As those things are sets, we have to show equality of sets. So that means whenever you have an element in one set, you have to show it's an element of the other set, and vice versa. So by the definition that A belongs to the equivalence class of, that B belongs to the equivalence class of A, that means that B is congruent to A mod n, and we also have A is congruent to C mod n. So then you have that by the transitive property that we just proved, B is congruent to C mod n by transitivity. So what does this mean? This means that B classifies the B satisfies the condition for it to be an element of the equivalence class of C, or the set determined by how we define this bracket C. So therefore, B belongs to the equivalence class of C. And the argument is the same if you reverse the ideas, all the ideas, and you reverse it, you get the other condition. There is one little bit tiny trick, but I will leave it for practice. So here you have that C is a subset of the equivalence class of A. So therefore, the equivalence class of A is equal to the equivalence class of C. Okay, so let's prove the reverse implication. So conversely, assume that the equivalence class of A is equal to the equivalence class of C. What we want to show that they are congruent, that A is congruent to C. But since A is congruent to A mod n, so that means that A is inside of its own class, which is equal to the class of C. So by the definition of the class of C, that means that A is congruent to C mod N, and we are done. So I will set up the following idea, and we can use this idea to develop more technical aspects of the theory that we're dealing with. So notice, we have the following remark. If A and C are sets, if you take the intersection, there's the following possibilities. So we have the following possibilities. The first possibility that the intersection is the empty set, so they are disconnected from each other. There might be that A intersection with B is non-empty, and it might be that A intersection with B is either A or B. So, well, the first option tells you that they are disconnected. The second option tells you that there might be common element between them. But the third option, so we're interested in really the option 1 and option 3. So the third option is that their intersection is not only non-empty, but it turns out that one of the sets is contained in the other one. So this congruence classes model those types of things, model 1 and model 3. So let's write down what we mean by that, and then we'll explore it. So we have the following corollary. Two congruence classes modulo N are either disjoint or identical. So what do we mean by that? It means that we either have no common elements, and if we have common elements between two classes, then they must be the same thing. So let's prove it. So assume that A and C, so if A and C are disjoint, then we're done. There's nothing else we can prove. So assume that we have non-empty intersection. We'll show that would give us, so we'll show that that will give us that the equivalence class of A is equal to the equivalence class of C. So since it is non-empty, there exists B inside of the equivalence class of A as well as C. So that means that B is congruent to A mod n, and B is congruent to C mod n. So let's flip things around. So here we have that A is congruent to B mod n by transitivity, by symmetry, and here B is congruent to C mod n. So then by transitivity we have that A is congruent to C mod n. So then by the previous theorem we have that the equivalence class of A is equal to the equivalence class of C, and we're done. So we're almost done with this subsection, so I will finish it off in the next video. And so I hope you guys enjoyed this one, and I'll see you in the next one. See you guys. Bye.